given situation of a 5 kilogram block on a level surface, we ask people to sketch pictures of the forces acting on it. Now, there's a horizontal force, and the thing is sitting on a surface, and that's pretty much all we know. So, what's the first force we can sketch? Okay, well, obviously, then of course the assumption is this is somewhere in the lab or somewhere at least in the vicinity of the surface of the Earth. So you have gravity pulling the thing toward the center of the Earth. Okay, you have 5 kilogram mass and you have gravity. You can easily figure out the magnitude of the gravitational force, and you know it's downward. Okay, and you have some horizontal force. You could draw that to the right or to the left. I chose to draw it to the right. I assume that the majority of the class in the class is about 70% left-handed, which is very strange, but very good, because the way left-handed people think is a little different than the way right-handed people tend to think and to visualize things, and it gives us a kind of a neat interplay. Anyhow, if you're left-handed, you should have drawn it this way, but if you didn't, well, it's okay. You're doing what you thought was the right thing to do. Seriously, it makes no difference whether you draw it this way or this way, because the statement of the problem just said there's a horizontal force, and it makes no difference if you put your x-axis in this direction or in this direction. You can do it either way as long as you declare which direction you're using as the positive x direction. Okay. Of course, now if we're going to do this on a coordinate plane, if you put your x direction this way, your coordinate plane needs to be a right-hand plane, so that your y-axis would have to be down here. And usually we draw it with the x-axis here and the y-axis here. But that's not carved in stone. There are reasons often why you want to do it differently. Okay, well, end of digression. We have a force straight down. We have a force in the horizontal direction. And no indication of how big or how small that horizontal force is. We just said there is one. So any arrow you draw in the horizontal direction and label in some way as your horizontal force is going to do the job. Now, at that point, we only had these two forces. We didn't have this force, we didn't have this force. And I asked the question, okay, well, if those, if those are the only two forces acting, in what direction is this thing going to accelerate? So, well, it's going to accelerate this way because you got a force this way and a force this way. That's right, but it doesn't accelerate this way because you got that tabletop there. What's that tabletop do? Well, that tabletop exerts a force that's normal to the plane. And we explained why. If something is being pushed into a tabletop, let's say, that tends to compress the tabletop. Now, if it's a uniform material, even if it's not a uniform material, but easier to think of a uniform material of uniform thickness, the compression doesn't have a preferred direction as to the right, left, to the right or left, okay? So there's a symmetry in the forces that are exerted on the tabletop to compress it to the right or left, and you have a symmetry in the compression. And the forces that you get, because you know when you compress something it pushes back, those forces push back in a symmetric manner that results in a force that's perpendicular to the surface. Okay? Or if it's a surface or some object that can be bent a little bit. Now, you bend it elastically, it snaps back again with a type of symmetry that causes the force to be perpendicular to the surface. Okay, so that's kind of a principle, that this normal force that results from the other forces pushing an object into the surface is going to be perpendicular to the surface. Okay, so the material itself exerts a normal force. Now, there's also the possibility of a frictional force, which is mentioned at the very beginning. And we say, well, if the thing happens to be moving across the surface, there's going to be a frictional force opposing the motion that's 60% as great as the force pushing the two surfaces together. Now we understand that the force pushing the two surfaces together is this normal force, so this frictional force should be 60% of this. Now if I want to draw that accurately for the 60%, I'm going to have to make this vector that represents the frictional force a little bigger. It's got to be 60% as big as this. It's probably about this big, so it should be about at least 50% bigger than I drew it. But this is just an indicative diagram, a generic diagram for an object that's experiencing a horizontal force here. There's a frictional force that opposes the motion, or a static frictional force that opposes the force in this direction, and would be equal and opposite if the object isn't moving. And we'll talk about that, but right now we're just talking about if the object is moving. Okay, so here's our diagram. These are our forces. Okay, so we calculate the gravitational force very easily. We multiply the mass by the acceleration of gravity. We find that we get a force of 5 kilograms times about 10 meters per second squared, using this approximation for the acceleration of gravity, which is 50 kilogram meters per second squared, or 50 newtons. And that's vertically downward. Now, the surface is horizontal. If the surface is horizontal, with these forces, the only other vertical force, other than the gravitational force, is the normal force. And there is no acceleration in the vertical direction. The object doesn't come up off of the plane because of a normal force that exceeds the gravitational force. The normal force is only what's necessary to prevent it from penetrating the plane, from falling down through the plane. And of course, it certainly doesn't accelerate in this direction because it would be penetrating the plane. So this force and this force have to add up to 0. Otherwise, you would have an acceleration either off the plane or into the plane. So the normal force and the gravitational force add up to 0. These are the only forces in the vertical direction. There's no acceleration in the vertical direction, so you have 0 net force in the vertical direction. And this then tells us that the normal force has to be 50 newtons vertically upward. Now, the question becomes, if this thing is going to move at constant velocity, then what does your horizontal force have to be? Well, by Newton's second law, the acceleration is equal to the net force divided by the mass. The question is, what's the net force going to be? It has to be 0. So the acceleration is 0, and the net force is 0. Again, assuming you're moving at constant velocity, because at constant velocity there's 0 acceleration. Knowing that